All right, we're going to start again. Any questions? No. All right, the hypothesis is a tentative fundamental description, and so that's what I should write here. It's tentative. And so typically what people do is they test the hypothesis and challenge it and see if they can further refine it. But once it's been refined and generally accepted, then we stop calling it a hypothesis and we start calling it a theory. Now theory, is what we're after. Because a theory is a fundamental description that has wide acceptance. But what can we do with a theory? You know, what we can do with theory is make predictions. And so that's the most important thing. What we want to be able to do is we want to predict things that haven't been seen without actually having to do an experiment to do that. And so let's just get to the end of the story. What is the theory underlying chemistry? Yeah, actually quantum mechanics. What describes the electrical interactions? Well, quantum mechanics describes the electronic structure, and in fact this is electronic structure around the nucleus, right? This is from chapter 8. You guys remember these things? Radial probability distributions? Or radial distribution functions? You know, quantum mechanics describes how the electron densities spread out over the atom or the molecules. And since chemistry just deals with electrical attractions, then we can see, you know, how the charge density is and how it's going to be attracted to other species, how it's going to react chemically, how it's going to react via IMFs, etc. But it's not so easy. I mean, let's say you wanted to apply the theory, okay? You know the theory, quantum mechanics. Now, predict the melting point of magnesium oxide for me. Is that easy to do? The quantum mechanics, the calculations are very tough. And so oftentimes those things are very difficult to do. They aren't so easy. In fact, oftentimes it's just easier just to memorize it. And so let's take a look at the lattice energies again. And so I want to ask you something. Okay, we have aluminum oxide. You know quantum mechanics is the theory underlying chemistry, so let's predict something. Tell me the chemical reactivity of aluminum oxide. Al2O3. What do you think? Well, you know, it really helps to have some numbers. So if we look at some numbers here, some experimental data, and so this is why in chemistry it's not just theory. A lot of people say there's no reason to memorize because in science you got the theory. No, there's lots of reasons to memorize. You have to memorize a lot of things in science. Otherwise you can't apply the theory. It's too hard to apply. And so when we look at something like aluminum oxide, well, we see a big lattice energy. What does that big lattice energy tell you? This stuff is going to be very hard to dissolve in water. Do you think you're going to be able to dissolve it in water? No. And then you can make some other, rough predictions, but what you really need is you need some kind of descriptive chemistry, some kind of chemical facts to really help you. And so let me give you some of these, and we're going to learn these as we go along, but You know, when I was an undergrad at UCLA, I took a graduate course in the engineering department. It was materials engineering. And aluminum oxide was one of the major topics of that class. Why? Because aluminum oxide is the wonder ceramic. This is called alumina, and it's used for a wide variety of applications. I used to use alumina all the time, and I'd buy it out of the catalogs. But what they had was they had alumina, not aluminum or aluminum, but alumina boats. And these alumina boats and dishes and bowls, and just it's like you're buying porcelain stuff, and you're gonna bake a casserole, right? And so I've got these alumina boats, and then I'd fill them up with different elements, and then I'd throw them in our furnace. We had a very special furnace. Our furnace is a platinum furnace. And why platinum? Because platinum goes to much higher temperatures than your typical furnace. A typical furnace, you heat it too hot, you're going to melt the heating element, right? With platinum, do you know what platinum melts at? 1600 degrees C. And so if you cook something at 1500 degrees C, which is enough heat to vaporize a lot of things, you know, you need something special. Well, the something special I used was alumina. Platinum, we also have platinum boats and gold boats too, because those have very high melting points. But the platinum, you know, is kind of soft. The walls, it was very thin-walled platinum, so I didn't like using the platinum boats. So I usually using alumina boats. And so I'd cook my stuff in there, get it to react, typically at 1300 degrees C, and cool it down, and then scrape it out of the alumina boats. And then I clean the boats. You know, these boats are very unreactive. It's like nitrogen gas. Do you know nitrogen gas is considered an inert gas? Why? Because that triple bond's so hard to break. And so it's very hard to get to react. Well, the same thing. Aluminum oxide, the ionic bonds in this are so hard to break. It's very unreactive. And so what I do to clean my boat off is I'd spray in some concentrated nitric acid and then cook it. So I'd get hot, almost boiling nitric acid and just clean it and look bright white again. You know, and this is extremely tough material. Single crystals of aluminum oxide are transparent. You know, when I was taking the ceramic class, I was reading one application of single crystal aluminum oxide. Single crystal aluminum oxide, it was used for nuclear bomber pilot goggles. They're transparent so you can see through them, and then they dope them with electrochromic material, so that if the photodetector sensed light, an intense light source like a nuclear explosion, it would block out all light through the goggles. So that's what one of the applications. And they would be safety goggles too, because it's a very tough material, very hard to break. Well, anyway, going back to this, there's lots of aluminum oxide on Earth. Aluminum oxide, for you geologists, what's this called? The mineral? Bauxite, right? And the planet's full of bauxite. And so this is something over the summer I was talking about, and I think I did it over the spring too, but, you know, where does all the aluminum metal come from? Do they mine aluminum metal out of the ground? No. Do you know where they get aluminum metal? They mine bauxite out of the ground and then convert bauxite to aluminum metal. Well, in the old days, aluminum metal was a precious metal because it was so hard to get this stuff to react. You know, in order to melt this, what do you think the melting point of this stuff is? Did it melt at 1600 degrees C? No. Stuff doesn't melt. And so, well, then you're going to need something more intense to melt it. Well, that's one way, because in order to refine that, in order to extract the aluminum metal out of this, I got to break it apart. I got to break the bonds apart. And so melting it is going to be very expensive. Well, let's try to dissolve it. What solvents can you think that will dissolve alumina? Do you think hot concentrated nitric acid will dissolve it? No. Boiling water? No. Strong base? No. Strong base and strong acids will touch it a little bit, but not much. And so this stuff is so unreactive and so tough, it's the wonder ceramic. If you take a ceramics class, they talk a lot about alumina because it is a great structural material and very unreactive. But if you wanted to get it to react, then that poses a big challenge. And somebody finally figured out how to dissolve alumina easily. You know how they figured out how to dissolve alumina easily? It has to do with hydration. You know, if you're thinking about hydrating, you want to form, you know, those nice, strong, hydrated ions. You know, those what we were looking at earlier. Oh, wrong. So do you know how they tackled this problem? Is what they try to do is they try to make these solvated ions even more stable. Now, how can you make these solvated ions even more stable? Well, you don't use water to hydrate it. You use something even more polar than water. Well, what's more polar than water? So you get a stronger ion dipole attraction. What's even more polar than water? That's a tough one, right? But you know what's more polar than water? Ions are more polar than water. And so it turns out that that what they did was they didn't use water to dissolve it or any aqueous solution. What they did was they dissolved the aluminum oxide in a molten salt. And so they looked for a salt that had a low melting point and that was common and cheap. Do you know what that salt turned out to be? Cryolite. And so you can mine cryolite out of the earth, you can melt it at a very low temperature. And so you get molten cryolite. And the molten cryolite can easily dissolve aluminum oxide without too much difficulty. And then once you get the aluminum ions broken off from the oxygens, then you can reduce those into aluminum metal. And so it turns out the person who discovered this, and you know everybody wishes they had discovered this because the person who there's a video of it too that sometimes I show in Chem 1A when I have time, but it's an interesting story because you never heard of the guy, but he was actually the richest guy in the world at the time because of this process. I forgot his name, but you can just look it up on the internet. I haven't shown the video in a while. But it's an interesting story, and chemically too, it's very interesting because the chemistry is simple, you know, but yet, you know, everything's simple after the fact. You know, getting there wasn't so simple. All right, so let's look at some other stories too. And one story is the story of complexes. And so Alfred Werner, this guy won the Nobel Prize for figuring out the structure of these complexes. And so what we're going to do is we're going to do a little bit more background because I figured this is good Chem 1A review, probably. And we can further illuminate what Werner did. And so let's go back to our story of the cobalt. Chloride. And look at the lattice. So I'm just going to draw part of the lattice. And again, this isn't an accurate representation. The coordination number is probably not 6 for each. And the coordination number is probably different depending on the lattice structure. And so I just have a crude representation of the lattice here. Like this. I expect this to have a fairly high melting point. You know, cobalt 3 plus, pretty high charge in there. And the solubility, the only thing that's saving me for the solubility is, on the one hand, I expect it to be fairly insoluble because cobalt 3 plus is highly charged. On the other hand, I expect it to be soluble because chloride is kind of a big, low charge density negative ion. And so that's tough. And so this is why we need to memorize some stuff. Rather than trying to do a calculation quantum mechanically, will cobalt 3 chloride dissolve in water? It's a lot easier just to memorize that. Chlorides bromides and iodides are all soluble except for silver, lead, and mercury. Now, you know, there are certain things that, let me do just an aside here. There's certain things that you go, didn't that just contradict what I said earlier? For example, silver and chloride. Silver is +1, chloride is -1. So why is this insoluble? You know, sodium chloride is soluble. Sodium is +1, chloride is -1. And so, why is this soluble? Oh, yeah. Why is it insoluble? Sorry, thanks. Why is it insoluble? Because, is it an exception? Yeah, it is an exception. But, you know, we want to get away from the laws. You know, the law says it works except for that. You know, and we want to start hypothesizing this. So we did. We came up with a hypothesis. You know, higher charge density, stronger, right? But that hypothesis wasn't enough. Because it's a little bit more complicated than that, because that brings up this, silver chloride. And so this brings up the theory. You know, just these simple electrical attractions isn't enough, because why do we have quantum mechanics? Why don't we just use Coulomb's law? Coulomb's law says positive and negative attract each other. We just look at the distance between the center of the charges. Coulomb's law is very simple. I like Coulomb's law because Coulomb's law says the force is proportional to the charge on body A times the charge on body B divided by the distance squared. You know, this is from physics. If you haven't done physics, this is a very simple equation, right? And so why don't we explain all of chemistry using Coulomb's law? Because, you know, Coulomb's law is more for point charges. You know, these point charges don't have any shape to them. We know that the charge densities that we're dealing with have shapes to them. In fact, you know, when we're looking at things that are close to 100% ionic, then Coulomb's law seems to work. But when we start getting to covalent things, then covalent things are a little bit more complicated. Because what do we look at? What makes a good, strong covalent bond? Well, triple bond's stronger, right? But why are some triple bonds stronger than other triple bonds? Well, the size, right? The certain sizes. But then you start looking, well, you know, I want a better fundamental picture of what makes a good covalent bond. So what is a good fundamental picture of what makes a good covalent bond? And we have two great fundamental pictures of what makes a good covalent bond. One of them is labeled VB for valence bond theory, and the other is labeled MO for molecular orbital theory. And so, well, what's the difference between MO theory and VB theory? Yeah, well, VB tries to predict charge density. So both VB and MO predict charge density, but we know that VB isn't very good. You know, VB failed miserably for what molecule? O2, right? So VB, you know, if VB failed miserably for that, why don't we just get rid of it? Because, you know what, one way of thinking about VB versus MO is the full quantum mechanical treatment of the bond, covalent bond. VB is the semi-quantum mechanical treatment. And so in my Chem 1A class, I labeled VB, valence bond theory, quantum mechanics light, and MO theory, quantum mechanics full, the full version. And the quantum mechanics full version, so let's just focus on quantum mechanics full version, MO theory. What makes a good bond in MO theory? You guys know what makes a good bond in ionic. We spent so much time talking about it, right? I think. But what makes a good covalent bond? Let's compare two single bonds. Well, in MO theory, what is the number one thing in MO theory? The primary. When we think about MO theory, LCAO comes up. You know, and LCAO is what? Close. Not lowest, though.
Linear.
The LUMO was the lowest. LUMO and linear combination of atomic orbitals. And so what makes a good linear combination of atomic orbitals? Because when we do the linear combination of atomic orbitals, we generate molecular orbitals. Remember the mixing of atomic orbitals to get the molecular orbitals. And when we form a molecular orbital, bonding molecular orbital, we also form a anti-bonding molecular orbital. And so what would form a more stable bonding molecular orbital? You know, what gives you the best in terms of stability for bonding MOs? And so this is something that you look for as far as the patterns go, but the pattern that people see, and this is easy to recognize, is something called hard, soft, acid-base theory. And what it boils down to is this. If I'm going to mix these two atomic orbitals, let's say I take a small orbital versus a big orbital. A small orbital, is it more polarizable or less polarizable than a big orbital? Big orbitals are more polarizable or less polarizable? What was polarizability again? Well, polarizability is the distortion of the electron cloud. And so which one's easier to distort the electron cloud? A big orbital or a small orbital? Big orbital. And so we say big orbitals are more polarizable. Now, in terms of hard and soft, are big orbitals soft or are big orbitals hard? Soft. Small orbitals, less polarizable, are hard orbitals. And so when we're thinking about this, small orbital with a small orbital, is that a good combination? Yeah, that's the best combination. Small orbital and a small orbital are going to make good, strong MOs and very destabilized antibonding. Now, it turns out that soft and soft is a good combination too. But soft and hard is a poor combination. You don't get good MOs from that. And so why this is insoluble is because of this. A lot of heavy metals aren't fully ionic. Silver is a heavy metal. A lot of heavy metal salts are quite covalent. These have a lot of covalent character in the bond. And because of the covalent character, then we look. This is soft, so it's going to form good MOs. Here, good MO interaction. And so this is an exception because we can't think of these heavy metal salts as being totally ionic. And for example, PbCl4. PbCl4, what's the charge on lead? Plus 4. So this thing should be highly insoluble, right? This should be impossible to break this lattice. But do you know this is soluble? Why? Why is PbCl4 soluble but PbCl2 not soluble? It's because PbCl4 forms molecules, because these are highly covalent bonds. Well, I shouldn't say highly. These have a high percentage of covalent character, a low percentage of ionic character. Do you guys remember the percent ionic, percent covalent thing from chapter 9, chapter 8? From chapter 9. These have so this forms molecules. PbCl2 forms an ionic lattice. This forms molecules because this is much more covalent. This is much more ionic. All right, so there are going to be certain little, but when we look at the full theory, you know, when we apply it, then it makes more sense. You know? But what we're doing is we're just learning some applications a little bit at a time. We'll come back to this because we're going to be talking about solubility quite a lot. All right, now let's do this. Do you know these spaces between the ions? What are these called? Holes or void spaces. And sometimes you can fit small molecules. One of the common small molecules you can fit in there is water. And so what happens is a lot of crystals pick up moisture from air. water molecule from air gets stuck in these voids and holes, and we form a hydrate. Like, for example, copper-2 sulfate pentahydrate. It's a solid, nice blue solid. I have some pictures of it, but I'm going to skip it for right now. But what holds a water molecule in the hole? An ion dipole attraction. Well, we could fit other molecules too. What's another polar molecule that we can stick in the holes or the voids of the lattice? Well, something else that is quite polar is ammonia. And so what we can do is, rather than hydrate, we'll get some ammonia in here. So we'll stick one ammonia in there. There, little void space there. We'll stick another ammonia in here. And so we'll get 2. And we could stick another ammonia in here. We could get 3. And so what do you think the maximum number of ammonias that we can put in there? Well, it depends. It depends on the holes, depends on other things. But for cobalt-3 chloride, it turns out we can fit in a maximum of 6. And so that's completely saturated. It's still a solid. And so, and so the way we visualize that is like this. We have the lattice of ions here, and then in these spaces between the ions, there are ammonia molecules stuck in there. Okay, we can get rid of the ammonia molecules. Tell me one way to get rid of the ammonia molecules out of there. One way to get rid of it is just to heat it up. We don't want to heat it up too hot, because if we get it too hot, we'll break the ions off. But if we heat it enough, we can break the interaction. Now, what is the interaction that holds the ammonia in the crystal? What type of force of attraction is this? Are the ammonias bonded? No. Are they hydrogen bonded? No. And so what type of... This is called a ion dipole attraction. We have ions, they're attracted to the dipole of ammonia. The dipole of ammonia looks like this. Ammonia is a polar molecule. And you have these trigonal pyramidal arrangement of hydrogen atoms. But the dipole of ammonia, there's a negative end here, a positive end here. The dipole looks like this. You can use an arrow to represent that. And so we have ion dipole attraction, so we just need a little bit of heat, and then we can drive off the ammonia as a gas. Just like a hydrated crystal. A hydrated crystal, you just got to heat it up a little bit, and you can drive off the waters, because those water molecules are just held in there by ion dipole. There's another way to release the ammonias. The other way we can release the ammonia is by dissolving this crystal. When we dissolve this crystal in water, we know it's soluble because chlorides are soluble. And even though, cobalt has a pretty high charge, 3+, well, this still dissolves. And when this dissolves, what happens? The waters collide with the ions. It breaks off the ions. So chloride breaks off here. A cobalt breaks off there, etc. Right? And so we get the hydrated ions. And these hydrated ions are free to move around. Well, when we break off the ions, that's going to free up the ammonias. And so we're going to get ammonia stuck in solution as well. And so we're going to have a mix. We're going to have a mix of the ions and ammonia molecules. Now, ammonia molecules, is it a strong electrolyte, weak electrolyte, or non-electrolyte? It's a weak electrolyte. It's a weak base. So ammonia is a weak electrolyte, but we don't want to show it dissociated. Well, this is the same thing you do when you write ionic equations and non-ionic equations. You only ionize the strong electrolytes. And so we leave this one intact. Okay, so now we have it. Now, there's some words. Did I talk about empirical units and formula units? Did I talk? Okay. Let me talk about that briefly. For every mole of COCl3, how many moles of ammonia? 6 moles of ammonia. Now, for every cobalt and 3 chloride ions, and so if I just pick out, 1 cobalt and 3 chlorides, like this, 1 cobalt and 3 chlorides. What do I call that? Do I call this a molecule, a COCl3 a molecule of cobalt-3 chloride? What should I call this unit here? I have 3 chlorides, so I pick these 3 chlorides and this 1 cobalt. Is that a molecule of cobalt-3 chloride? No. There's no molecules here, right? Because there's no distinct or unique COCl3 unit. I could have picked this cobalt and 3 other chlorides. In other words, I'm going to call this an empirical unit or a formula unit, and the common term is a formula unit. And so for every formula unit of COCl3, how much ammonia? 6 molecules of ammonia. Okay. All right. Now let's do that. So I'll get 3 chlorides, 1 cobalt, and then 6 ammonias in here. Saturated. Have you ever done gravimetric analysis? We had a lab like that. It was called the sulfate lab. Yeah, everybody's done it? Yeah. Okay. What you do in gravimetric analysis is once you get everything broken up, you want to isolate it. And so what I want to do is I want to do gravimetric analysis of chloride. So what I do is I try to isolate the chloride from everything else. And so I want to pick something that reacts just with chloride and nothing else. Is there something that reacts just with chloride and nothing else? Sodium? No. If I had sodium there, then the sodiums would just be floating around solvated sodium ions. Silver. Silver ion reacts with chloride. Do I need this anymore? I'll turn it off. Okay, so one way to analyze this solution is I'm going to add excess silver ion. You know, maybe silver nitrate or something like that. And when I add excess silver ion, the silver ion should attack the chlorides and precipitate. So for every formula unit of cobalt-3 chloride, how many formula units of silver chloride will I generate? 3. And so I should precipitate out 3 formula units. For every mole of COCl3, so I'm going to precipitate out 3 moles of silver chloride, just stoichiometry. Okay, is that good? The rest of it we'll just ignore. You wash in gravimetric analysis. You filter out the rest of it and then wash your crystals and get rid of all the other junk. So you're left with just silver chloride. That's what you do. And so the other stuff would be still there, but in the waste jug by now. All right, so I don't have to add 6. Let's only add 5 NH3s. If I add 5 NH3s, then there's going to be an empty void. But that's okay. You can have empty voids, can't you? Yeah. This is the solid. And so I visualize this in the exact same way. You know, I have a lattice and the void spaces, but I haven't saturated all the void spaces. In other words, I'm just going to expose it to a little less ammonia. And when this dissolves in water, what do I expect? Well, when it dissolves in water, I expect to break apart the lattice and free up the ammonias. And so it breaks apart the lattice, so I get the cobalt-3 in solution, chlorides. And rather than 6 ammonias, I'm going to be left with 1, 2, 3, 4, 5 ammonias per formula unit. And so this is what you do in gravimetric analysis. You know, we want to analyze that for chloride. We dissolve it, free up the chlorides, and then isolate them by adding excess silver. And what do we expect? How many silver chlorides? 3. And so we predict 3 silver chlorides to precipitate. But that's not what was observed. What was observed is only 2 silver chlorides precipitate, no matter how much excess silver ion you add. And so they didn't get 3, they got 2. Well, that means there's something wrong with all the theory and hypothesis and whatever else I've been talking about for the last couple of days, right? There's something wrong in this picture. And so this is what people were thinking with these hydrates and these ammoniated type crystals. Can I start taping? And so what was wrong with this? What was wrong is this. When we're trying to predict chemical reactions, you know, how many chemical reactions, how many different kinds of chemical reactions occur in the universe? 3. Just only 3? Wouldn't you say billions? I mean, if you think about it, billions. Actually, let me just take a brief survey because, and I don't want people to, I'm going to skip some people, so don't feel ignored, but I just want to get an idea. How many types of chemical reactions occur in the universe? Basic types. Maureen? What do you? Yeah, combustion, precipitation. What else? How many? Decomposition. So we got 3: combination, redox, single replacement, double replacement, mutualization. Double replacement. Already said that? Oh, yeah. So let's eliminate. 7? We'll go with 7. All right. Mackenzie? What do you think? How many? How many types of chemical reactions? 3. Jay? How many?
I said
8? Okay.
Can you say metathesis?
Yusef? Arb? All right. Well, you know what? We don't have that much time, so I'm going to skip the survey right now. But basically, you know, you wouldn't be wrong if you said 7. You wouldn't be wrong if you said millions, you know, or billions, because there are a lot of different chemical reactions that occur. But when you start classifying, okay, let's say you say 7, then, you know, it becomes hard to predict. A long time ago when I was a graduate student at UCSB, a student came in, and I was holding my office hours as a TA, and they asked me, you know, how can I predict what the products of this are? And then I thought about it. They gave me, you know, they had a general question. When I mix these 2 chemicals, how can I predict what the product is going to be? And then, you know what the answer I told him? I think I literally told him, oh, from experience. He wasn't happy about that answer. But then I thought, you know, maybe, you know, that isn't a great answer. You know, I've seen it. I've seen lots of different reactions, but I didn't have a good classification scheme because I learned the same thing you guys learned, you know, combination, decomposition. But when it comes to predicting, I saw a lot of exceptions, you know, and so what I'm going to show is a different classification scheme we're going to talk about this semester. And the classification scheme, there's 3 types of reactions, the 3 main types of reactions. This isn't a classification scheme I developed. This is a classification scheme I learned after I talked to the student. Then after I talked to the student, I took this class, Advanced Synthetic Chemistry class. And I read the book and I thought, wow, this is a good book because of how they organize chemical reactions. They organized it into 3 categories, and I thought it just made so much more sense than the Gen Chem book we were using. And so in that case, the grad course was a lot easier than the Chem 1A course in predicting chemical reactions. It was way easier. And so this is why I thought, well, why not just teach it now, because it is easier. But a lot of people get psyched out and think it's a lot harder than the other categories. But anyway, going back to this, what are the three? Well, there's something called metathesis. Metathesis are ion combinations or double replacement. This is a metathesis reaction. Silver ions like chloride ions form a nice strong bond. Good lattice. There's redox reactions. Silver ions are a good oxidizer. Ammonia might react with silver ions in a redox. And then there's acid-base reactions. Most of the acid-base reactions you're comfortable with, like sodium hydroxide, HCl, right? But there's another category. There's actually three categories of acid-base reactions. There's Bronsted-Lowry acid-base reactions. Bronsted-Lowry acid-base reactions are very simple to predict. The reason they're so simple to predict is because we have a Bronsted-Lowry acid-base chart. The strongest acid on the chart is in Chem 1A. Do you guys remember what the strongest acid is on the chart? Not hydrochloric, not sulfuric, not HI, not HF. HI is actually weak. Not HI. HCl4. I knew you were going to get it eventually because there are only 7. But 7 common strong acids. So perchloric's at the top. That's the strongest acid. What's the strongest base on the chart? Acetic acid is LiOH. The strongest base. Hydroxide? CH3 minus is on the chart I gave as a handout. But what was the strongest base in the chart?
Amide.
Amide, right? Or amide, if you want to call it that. Amide was the strongest base on the chart, right? And then if we have the chart, then we can easily rank the acids and bases. And so that's easy. Because all we're looking at is what makes a good Bronsted acid. A good Bronsted acid is a good proton donor. A good Bronsted base is a good proton acceptor. Well, the next type of acid-base reaction is a lot harder because we don't have a simple chart like that telling us the strength. And the next type of acid-base reaction that I want to talk about a lot this semester is the Lewis acid-base reaction. A Lewis acid base, well, what is a Lewis acid? What's a Lewis base? Yeah, a Lewis base is electron pair donor. A Lewis acid is electron pair acceptor. And so if we look at this mix, do you see a Lewis acid or Lewis base present? Well, I see Bronsted, ammonia. I see water. Water is amphoteric. There's both an acid and a base. Actually, ammonia is amphoteric too. And so I see some Bronsted, but what about Lewis? Oh, well, I do see some Lewis bases, like chloride. Is chloride considered a Bronsted base? Very weak. It's so weak we pretty much ignore it. You know, if you wanted to neutralize your stomach acid, let's say you had too much stomach acid and you're thinking, oh, I'm just going to take some sodium chloride. That should neutralize the acid. Is that going to be very effective? No. But chloride is considered a Bronsted base, but it's so weak we ignore it. But it's also considered a Lewis base. It's a Lewis base because if you look at it, Lewis bases are electron pair donors. So electron pairs, they can be donated. What else? Ammonia. Ammonia, the nitrogen has a electron pair. What about water? Water has 2 electron pairs. Okay, electron pairs are associated with negative charge. Now, which one of these is going to be the strongest? Lewis base, present. Chloride with a full negative charge, ammonia with a partial negative charge, or water with a partial negative charge. which one should be the strongest Lewis base? Well, you know, I would think the one with the highest negative charge, because the one with the highest negative charge will easily donate electron density, right? Because it's kind of electron rich. It's got a lot of negative charge density. And so, you know, in one sense, I would say that chloride is the best Lewis base. Wouldn't you agree? Would you agree or not really? We could also look at it in terms of Bronsted bases. What's a stronger base than hydroxide? Amide, but there are others. And so hydroxide is one of the strong bases on the chart. What are some of the other strong bases on the chart? What's stronger than hydroxide? Okay, what's weaker than hydroxide? Well, one base that's super weak is water. Now, why is water a much weaker base than hydroxide? Because water only has a partial negative charge on oxygen, whereas hydroxide has a full negative charge. And so you should know one base that's stronger than hydroxide that's on the chart. What is it? This is the Chem 1A chart in the classroom. What is it? It's good you remember amide. That's good. Amide, you know, amide is a way stronger base than ammonia. Amide has 2 lone pairs on the nitrogen and a full negative charge on the nitrogen. Ammonia has 1 lone pair on the nitrogen and a partial negative charge. Which one's going to be a more powerful base? A base is a proton acceptor. A proton's H+. H+ is going to be more attracted to the partial negative or the full negative? The full negative. So this base is going to attack this. Right? Versus this base is going to be weaker. And so if there's a competition between bases, this base is going to be the winner. For sure. Water versus hydroxide. Hydroxide is going to be the winner. If there's acid around, hydroxide is going to quickly pluck that up versus water. And so what was a stronger base on the chart? Do you guys remember? Carbonate's weaker. Well, let me tell you. Oxide. Oxide is a more powerful base than hydroxide. Oxide has a lot of lone pairs. In addition to that, it has a 2- charge versus a 1- charge. Do you see oxide is going to be a much more powerful base? So if you have a competition, who's going to win? Oxide. In fact, oxide is powerful enough to pluck hydrogen off water easily. And so oxide's not stable in water. Oxide will react with water immediately to form hydroxide. It's called the leveling effect. All right, so going back to this question, we have 3 potential bases here. Which of these 3 do you expect to be the biggest? Well, okay, chloride. Okay, ammonia versus water. Which one? Water. Why water? Well, because on one hand, oxygen versus nitrogen, which one's more electronegative? Oxygen. So if oxygen's more electronegative, that builds up a bigger delta minus than nitrogen. Oxygen's electronegativity is 3.5, and nitrogen is 3, I think. And so I'd expect it to go in this order here. But you know, that's not what we typically see for Lewis acid-base reactions. Do you know what the strongest base that's present here is? You know, the strongest base that's present turns out to be ammonia. In fact, for a lot of Lewis acid-base reactions, ammonia versus hydroxide, which one do you think is more powerful? Ammonia or hydroxide? I think hydroxide. But do you know what you see in a lot of these Lewis acid-base reactions? It's not hydroxide, it's ammonia. Now, why is that? Well, why that is because we're only looking at it electrostatically. What we have to do is we have to look at what makes a good covalent bond. And so we got to look at how the orbitals do their LCAO. And when we do that, then we can see, yeah, then it makes sense that ammonia, because it forms good strong MOs. Good strong MOs is high bonding density. And so it gets a lot more tricky, because how often do you use LCAOs? And how often do you think about big orbitals, small orbitals? Never, right? You don't think about that. And so this is going to be the beginning. We're going to start thinking about things a little bit. But in order to start thinking about this, we need to build up the observations first. We aren't going to go straight to the theory. We're going to look at the observations and then see patterns in those observations and then just remember the patterns. Because applying theory, let's say we didn't memorize anything and we tried to apply theory, well, how easy is it to draw MO diagrams? You didn't do anything this complicated. The most complicated thing you did with MO diagrams are diatomic molecules. You never did a tetraatomic. You didn't even do a triatomic molecule. And so it's not so easy to apply. So what we're going to do is we're going to look at the patterns and remember the patterns and then apply the patterns to this. Well, it turns out that, you know what? Before this can react, what happens is there's a Lewis acid-base reaction. So I'm going to cut down to what happens here. Okay, so this is going to be the best. I'm just telling you, it's kind of hard to predict based on what you know. But ammonia is going to be the most powerful Lewis base. Now, Lewis acid is an electron pair acceptor. Do you see a Lewis acid here? Well, water is a Lewis acid. You know, water. Cobalt. Cobalt's a Lewis acid. Now, how many valence electrons does cobalt have? Cobalt 3 plus. Zero. And so when we think about cobalt 3 plus, I just think of a ball, a sphere that got the 3 plus charge on it. And so what's going to happen is the ammonia sees the base here, ammonia sees the acid, cobalt, and we have a Lewis acid-base reaction occur. And so the ammonia comes in here and boom, attacks the cobalt. Usually in chemistry jargon, the base attacks the acid. So we get this. Now what happens when the base attacks the acid? Now what happens is this. We form this. We got the cobalt here, and now we got an ammonia. And so here are some names for this. This is the Lewis base. Sometimes, depends on the context. The Lewis base can also be called the ligand. I'll talk more about ligands later. The cobalt 3, this is our Lewis acid. And the product of this reaction is called an adduct. The Lewis acid-base adduct. Now the adduct is kind of weird because take a look at this bond. Now how does a bond form? When we typically think of bonds, we think of valence bond theory. Valence bond theory is overlap of atomic orbitals. Or we think about MOs. You know, what MOs are doing the linear combination of atomic orbitals? Well, what I'm going to tell you is don't worry about the bonding for this. In fact, you know, when I think about this, I think about formal charge too. You know, automatically I'm looking at nitrogen. This nitrogen looks like the nitrogen in ammonium ion. And that nitrogen has a positive formal charge. So if I look at this nitrogen has a positive formal charge, and the charge on cobalt just dropped. It was +3, but now it has an extra electron. If it has an extra electron, the charge is now +2. And so it went from +3 cobalt to +2 cobalt. Do you see that? That's formal charge. But we don't count the electrons this way. And so there are actually going to be 4 ways of counting electrons. Way number 1, formal charge, oxidation state is 2, octet is 3. Now for these complexes, that's 4. For these complexes, we do a weird thing about counting electrons. The way we count the electrons in a complex like this is cobalt still has, even though we got this, and this is, you know what this is, actually, let me talk about counting electrons right after I write this down. This is a coordinate covalent bond. It's also called a dative bond. The only difference between a regular covalent bond and a coordinate or dative covalent bond is that both bonding electrons come from one atom. In a typical covalent bond, one atom supplies one electron, another atom supplies another electron, and then they share them. That's a typical. But in a coordinate or dative, both electrons came from nitrogen. Cobalt contributed no electrons. And so the way we count the electrons is kind of funny. We call cobalt still 3+, and we call ammonia neutral. Even though this looks like ammonium and we get a positive formal charge on nitrogen, we're just going to say it's neutral. And so that's the fourth way of counting electrons. Well, you know what? This cobalt is susceptible to another attack. A second ammonia can come over here and bind to it. There. And so what we end up with is now we got to two cobalts. I mean, not two cobalts, two ammonias bonded to this. Like this. Now, what's the charge on cobalt? Well, if you're thinking formal charge, now the cobalt charge should be +1. But we don't count it that way. The cobalt's still 3+, and the ammonias are still neutral. Well, if you're another ammonia, you know there's still space here. We can attack it some more. And so eventually, what's going to happen is, it depends on the ions and it depends on the bonding, but typically a Lewis acid like this can be attacked by 2 to 6+ bases. And so for cobalt, we end up with a structure that looks like this. It's going to be octahedral with, when it's saturated, 6 ammonias covalently bonded. And it's the nitrogen that bonds, so this is why I'm going to write this ammonia backwards here. Yes. This has a 3+ charge. And this is called a complex ion. And so rather than the ammonias held to the cobalt by an ion dipole attraction, they're actually held to the cobalt by an actual bond, a covalent bond, which is quite a bit stronger. Okay, this doesn't happen in the water. This actually happens in the solid phase. When the ammonia seep into the crystal, the ammonias actually bind to the cobalt in a Lewis acid-base reaction. And when we saturate it, we can bind or bond 6 ammonias to that. And that leaves 3 chlorides out here because we got to counterbalance. This is one gigantic cation. It's a polyatomic cation. And now we got to surround that by our anions, like this. And we make up a lattice of alternating cation and anion. And so we'd have another cation here, anion here. All right, so now when we take this solid, okay, so the ammonia attacks it in the solid phase. And so to drive off the ammonia now, we have to break off the covalent bonds here. So that's going to require a bit more heat. It's not going to be as simple, just heat it up gently, the ammonias are driven off. It's going to be, you got to break off these Lewis bases that have bonded to it covalently. But we can still dissolve this in water. In fact, this might be easier to dissolve in one respect. It should be easier to dissolve because now we got this big clunky 3+ cation, whereas before we had a very small, hard 3+ cation. On the other hand, it should be harder to dissolve because solvating this big clunky ion is more difficult than solvating a small compact ion. but nonetheless it still dissolves. And so when this dissolves, the chlorides break free, and so we got these hydrated chloride ions floating around. But do the ammonias break free? When you dissolve it, when you dissolve this in water, do the covalent bonds break when you dissolve it in water, or do the covalent bonds stay intact? And so I dissolve this in water, will those ammonias break off? Like diamond, when you dissolve diamond in water, well, does diamond dissolve in water? No. Why? Because it's covalently bonded. And so this, when you dissolve this in water, you get these big clunky cobalt with 6 ammonias attached to it, plus 3 cations. And those ammonias are stuck to it. And so this is just one unit. Mm-hmm. It's because they're covalently bonded.
The overall molecule has a charge of 3+, so
Yeah, this whole thing has a charge of 3+.
how come it doesn't change?
Right, because when it forms heterolytically. It forms heterolytically because of this. When it forms, both electrons come from one atom. So here, atom A, atom B. Normally, it forms homolytically. You know, atom A contributes an electron, atom B contributes an electron, we form an A-B covalent bond. This is a coordinate covalent bond. Both electrons come from atom A. You can't tell the difference. You know, these are both the same, whether formed homolytically or heterolytically. If these atoms are the same A and B, then you can't tell the difference. It just looks like any other normal covalent bond. When you break covalent bonds, you break them typically down the middle, right? What causes both electrons to go back to A? To break it heterolytically. And so typically, there are 2 ways to break a bond. You can break it homolytically or heterolytically. And if it's covalent, it's usually homolytically, because there has to be a big difference in electronegativities of the species to cause it to break heterolytically, a covalent bond. In other words, it has to have a lot of ionic character to break heterolytically. It's got to be close to ionic. And so what that means is that if we break these down the middle, these are just like carbon atoms. They're neutral. They aren't polar. Are they going to dissolve in water easily? Well, not the cobalt. I shouldn't say. That wasn't the great example. But in other words, these aren't so easy to break by water. Now, this example would be better for water. Okay, so one example of this would be something like NO. You know, when you dissolve nitrogen monoxide in water, does it break up into nitrogen atoms and oxygen atoms? Or O2. When you dissolve O2 in water, do we get single oxygen atoms and single oxygen atoms? No. And so it's the same thing here. We aren't going to break it up. Okay, that's okay. And then we add our excess silver. The excess silver is going to attack the free chlorides, and we're going to get 3 silver chlorides. So, like this. All right, let me talk about this. What if we're looking at this COCl3.5NH3? If we looked at COCl3.5NH3s, those NH3s aren't trapped in the void spaces. Those NH3s are going to attack CO. And even though this is in the solid state, and so what's going to happen is the CO is going to be attacked by 5 NH3s. And so let's just put them in here. What's the charge on CO? It's 3 plus. And so what that means is there's an empty spot here susceptible to attack. And so we got to think, are there any other bases around? You know, we had chloride is around, and we have water that's around. And so what's a stronger base, chloride or water? It turns out chloride's a stronger base. And so since there's no more ammonia left, the next strongest base will attack here. And the next strongest base attacks, we end up attaching a chloride. And we form a coordinate covalent bond with chloride rather than ammonia here, just because there's no ammonia. Now this bond's interesting because this is no longer an ionic bond, this is a coordinate covalent bond. And so when I'm visualizing this, we got to write the formula differently. And so what Werner did is he said, well, we shouldn't write it like this, we should write it like this. COCl NH3 5 Cl2 solid. And so when I think about this crystal, then I think, okay, I got this, and ammonia, I'm just going to abbreviate AM, just to save some time. AM. Okay, now the way we count electrons is very weird, again, because cobalt, what's the charge on cobalt here? 3 plus. What's the charge on chlorine here? -1. And so the net charge on this complex, the ammonias are 0, so the net charge on this complex comes out to 2 plus. And so the solid is just going to be alternating 2 plus cations with 1 minus anions. And so I'll need 2 chlorides for every cation. Balance, and then I'll just alternate them. Will this solid dissolve in water? Yeah, it's a chloride salt, so it dissolves. When it dissolves, we break apart the chlorides from the cation. So we got chlorides floating in solution, and now we got the cations. Now, do the ammonias break off? No. Does the chlorine break off? This chloride, does this chloride break off? No. And why? Because it's covalently bonded. And so what we end up with are these solvated complex cations. And the chlorine is stuck on there. And so now when we add our excess silver, rather than getting 3 silver chlorides, we're going to only get 2 silver chlorides. As only 2 of the chlorides were capable of breaking off. The third one wasn't. And so these are examples of complexes, and we have to name these things. And so the name, let's go ahead and name the first one we were looking at, and then I'm going to end early since I skipped the second break. Okay, the first one is going to look like this. It's CONH3 6 3 plus. And the way we name this is we're going to name it hexa for the 6. And then ammonias have a special name. They're called amines. And so rather than do a double vowel, which you can't, hexamine, we're just going to call it hexamine. Hexamine. Now there are 2 amines. There's an amine with 2 M's, and there's an amine with 1 M. We'll talk about the difference in just a second. This is going to be the amine with 2 M's. And then there's no space. It's going to be hexamine cobalt 3 ion. fix it. Ion's optional. All right, this Roman numeral 3 does not refer to this. The Roman numeral 3 refers to the 3 plus charge on cobalt, the oxidation state of cobalt. The hexa refers to that. The amine refers to the ammonias. Okay, the two amines, we have one amine, which is ammonia. We have another amine with a single M. The single M amine refers to ammonia analogs, where we replace the hydrogen with something else. So rather than say NH3, I'm going to call it NR3, where R is, it could be hydrogen or carbon, typically. And so an example of the single M amine, the single M amine would be something like this. It'd be CH3NH2. Have you ever seen this? CH3NH2? Yeah, methylamine. And amines are very similar to the amine or ammonia. And that is because of this. When we look at it structurally, it looks quite similar. It looks like ammonia. The only difference is it has a carbon rather than a hydrogen here. And so the organic bases, weak bases, which we call amines like methylamine, is going to mimic ammonia. This is going to be a lone pair donor. This is going to have a delta minus charge here. When we compare that to ammonia, it looks the same. Now, I want to ask you, which one do you think is a better base? Do you think ammonia is a better base or methylamine is a better base? Well, you know, they're going to be quite similar. The reason they're quite similar is because of this. The delta minus is determined by differences in electronegativity. Nitrogen is 3, hydrogen is 2.1, so we get some delta En, right? The only difference here is rather than having a hydrogen, we have a carbon. Hydrogen is a 2.1. What is carbon? 2.5. Good. Remember it. And so, is 2.1 and 2.5 a significant difference? No. You know, 2.1 and 2.5 are thought of as being very close to each other. And so when we look at something like this, is that a polar molecule or a nonpolar molecule? It's a nonpolar molecule. The reason why this is thought of as nonpolar is no matter what the shape of a hydrocarbon is, the difference in electronegativity between carbon and hydrogen is relatively insignificant. It's only 0.4. Therefore, a carbon-hydrogen bond is fairly nonpolar. Okay, so that means that a carbon pulls about the same as hydrogen. And so both of these have about the same base strength. Now what we want to do is we want to really nitpick on this. Well, you know, I know they're both going to be about the same, but which one will be just slightly better? Which one do you think will be slightly better? Why do you think methylamine will be slightly better? Okay, the next thing I'd look at is this. Having a 2.5 means that carbon is going to pull more on the electron density than hydrogen. Hydrogen pulls less on the electron density. And so when I look at the bonding electron cloud here, the bonding electron cloud is going to be more polarized here. It's going to be pulled closer to nitrogen because it's a tug of war for electron density, and carbon is a stronger opponent than hydrogen in fighting for the electron density with nitrogen. And so when I look at this, I expect the delta minus here to be bigger than the delta minus here, based on delta En. This is going to be a smaller delta En, therefore it's going to be less polar. This is going to be a bigger delta En, therefore it's going to be more polar. And so as far as base strength goes, I'd expect, based on electronegativity, that ammonia should be the better base. But you have to always be careful using electronegativities because, and I try to do this in Chem 1A. You always have to be careful using electronegativities because, let's look at this. Chlorine versus chloride. Do they have the same electronegativity? Which one's more electronegative, chlorine or chloride? What is electronegative? Electronegativity is pull for electrons. So which one's going to have a stronger pull for electrons, chlorine or chloride? Chlorine. I mean, chloride's already electron rich, so or richer than chlorine. And so chlorine has a greater electronegativity. Do you see that? And so even though it's chlorine, it depends on its electron environment, right? Well, even though this is carbon, it depends on its electron environment. Do you know which one turns out to be a better base? You know which one's the better base? Between these two. I just told you ammonia is expected to be the better base. Why?
Higher delta negative.
Higher delta negative. But do you know which one's the better base? Methylamines the better base. Why is that? It's because we don't just look at electronegativities alone. If you look at electronegativities alone, you might be fooled sometimes. So for example, chlorine versus chlorine in perchlorate. You know, are they going to have the same electronegativity? No. Why? Because it depends on the bonding environment. This chlorine versus this chlorine are totally different. Chlorine is a powerful oxidizer, right? Chlorine gas, Cl2. That's this chlorine. Perchlorate is a much more powerful oxidizer. Why? Because this chlorine is quite a bit different than this. This chlorine, but it doesn't look different. How is it different? Well, it's different because we got to look at how the electron environment is. And there are three common ways of counting electrons. What are the common ways of counting electrons? Formal charge, oxidation state, and an octet. Well, I'll tell you why this carbon doesn't behave as like a carbon at 2.5. You know, a carbon at 2.5 would be like diamond. This carbon is quite a bit different than the carbon in diamond. Because if you look at diamond, what's the oxidation state of carbon in diamond? Well, the oxidation state of an element in its elemental form is 0. So the oxidation state is 0. And therefore, I'd expect this one to be 2.5. But when I look at this, the formal charges are all 0. And so formal charge doesn't tell you anything. But when you look at the oxidation state, what is the oxidation state of this carbon here?
4, 3, 0. No.
No, not 0.
This is 4, 3, -2.
-2 is correct. The oxidation state of this carbon is -2. And so you're comparing a -2 carbon to a 0 carbon. Are they going to have the same electronegativity? No. In fact, this carbon is much more electron rich than this carbon. It being much more electron rich, it isn't going to be nearly as electronegative.
How is it -2?
Oh, how is it -2?
Oh wait, never mind. Yeah, tell me too. Wait.
how is it minus 2? It depends. It's how we divide up the electron. With oxidation state, winner takes all. You assume the bonding is 100% ionic. And so winner takes all mentality. If there's a tug of war for these two electrons, carbon versus hydrogen, who's stronger? Carbon. Carbon wins all. So carbon just won those two electrons. Carbon versus hydrogen? Same thing. Carbon versus hydrogen? Same thing. Carbon versus nitrogen? Nitrogen's stronger. Carbon's the loser. That gives 1, 2, 3, 4, 5, 6 electrons to carbon. So carbon now has 6 electrons. How many electrons does it normally have? Valence electrons. 4. So if it has 4 normally and it has 6 here, then it's gained 2 extra electrons. 2 extra negative charges means minus 2. That's how you calculate it. And so what that means is that this methyl group is what we call an electron pusher. It's electron rich. And so what it makes is it makes this nitrogen even more basic. And so it turns out that the negative charge density on this is actually bigger than the negative charge density on that. And so, you know, we're going to get practice using all these tools that you learn in Chem 1A and Chem 1B as we go along in the course. So these oxidation state stuff, we're going to be doing a lot of these. So, formal charge, a lot of those. Lewis structures, a lot, because we're going to be dealing with Lewis acid-base reactions, so we need to know Lewis structures. We need to know covalent bonding. We need to know that kind of stuff. So that's good stuff to review. And you know what? I just ran out of time to do the quiz, so we're going to have a quiz tomorrow. All right.